Hello everyone, welcome back to The Game You Can Win, but Cannot Play. In this episode, we're going to be looking at another topological game. Now this topological game it's a very common variation on the Banach-Mazur game. However, it doesn't really have a canonical name, so to speak. In fact, a lot of the sources I've found just called it the Banach-Mazur game because it's sort of a more elegant and easier to study way of looking at the Banach-Mazur game. But we're calling it BM of X, as per a paper by Telgársky. Alright, so at this point, I think we're all pretty clear on what a topological game is, and how, broadly speaking, they are played. So let's just jump straight into the rules of BM of X. This weird modification, streamlining, sometimes it's called the Banach-Mazur game of the Banach-Mazur game. Now you can see that it's streamlined because, as opposed to the Banach-Mazur game, where you had to have a topological space, a subset of that space, and a class of subsets, here, all you need is just a topological space X. Super easy. Quick and easy setup. That's always an advantage in board games that people like to advertise. Anyway, here's how you play BM of X. So, player 1 starts off by looking at X and just choosing any non-empty open set in X. Then, player 2 chooses their own open set in X, so long as that open set is, of course, a subset of what player 1 just played. Then, player 2, where am I? There we are! Ha ha ha! I got it! Yay! Yes, player 1 chooses an open subset of what player 2 just played. So maybe it's a disconnected open set. Ooh. Then, player 2 chooses an open subset of that set that was just played. And then player 1 chooses an open subset of that, and so on and so forth. Ad infinitum, and at the end of infinity, we say that player 1 wins the game if and only if the intersection of all these sets, or equivalently, the intersection of every one of a particular player's sets, is empty. So what you might notice here is that this game is effectively identical to the previous one we talked about, MB, X, Y, script W, except that now, we're calling our topological space X instead of Y. The subset of the topological space we're interested in is just the entire topological space, and the class of subsets we're restricted to choosing is every non-empty open set in our topological space. And then the only other difference is that the win conditions are kind of reversed. So now player 1 wins if the intersection is empty, as opposed to player 2 winning if the infinite intersection is empty. So, that's BMX. It's like MBYY, topology on Y without the empty set, but backwards. Now, in spite of this modification being, super duper subtle, it actually changes the dynamic of the game a whole lot. Alright, so at this point, I think we're comfortable enough with how topological games are played that we can just jump right into the strategy of BM of X. And to do so, we'll still need to define some terms, but thankfully we only need to define one this time, the Baire space. A space is Baire if every open set in it is non-meager. There are also some other ways to characterize it. For instance, a set is also Baire if and only if Every countable intersection of open dense sets is also dense. But in any case, one famous example of a Baire space is the real number line, which might be what we expect. The real number line is the real number line is a very nice space, and this Baire property seems like it's very nice. Meanwhile, the set of rational numbers with the subspace topology is not Baire, as any open set on it is going to be meager, because every open set on it is the countable union of singleton sets, sets containing exactly 1 point, because after all, Q contains a countable number of elements in it itself. So there are open sets on it that are meager, so Q cannot be Baire. Now, player 1 in BM of X has a strategy if and only if X is not Baire. So, what is that strategy if X is not Baire? And well, as you can see, it's a little bit complicated. I'm going to try and explain it as best as I can, but be forewarned. Firstly, since I'm kind of doing these videos off the cuff, my explanation might be a little bit... I might stumble over myself, is what I'm trying to say. Secondly, I'm going to go through it kind of quickly, so if there's a logical leap in here that you don't understand, you should probably do... I advise that you do the things that mathematicians, at least, or I guess I say mathematicians, but really just myself, the things that I do whenever I encounter a step like that in a proof. Either A, think it through yourself, try and justify to yourself why this logical leap is justified. Or B, just say to yourself, oh, yeah, that sounds okay. I can believe that. Moving on now. So without further ado, what happens if player 1 is playing BM of X and the space therein is not Baire? Well, what they're going to do is they're first going to take any old meager open set in that space, and we'll call that set X. Remember, this space is not Baire, so such a set must exist. Now, if we're trying to do a concrete example, then maybe we can say that, if we're doing a concrete example in Calvin's back, I don't know. Then we can say that X is Q, and this meager open set in Q is the open interval from 0 to 1, intersected with Q, of course. Now, since S is meager, we can write it as the union of a whole bunch of nowhere dense sets. Alright? We've done that before, so maybe we say this is, 1/2, union 1/3, union 1/4, union 2/3. Oops, I've accidentally been writing intersection signs there. And so on and so forth. Now, we define a collection of sets T, where T naught, we just let that be X, and T sub n is equal to, whoops, this should be S here. Like I said, making some mistakes, stumbling over myself, whatever. S, but with the closures of all of the sets S sub I up to a certain point, up to a certain number, removed from it. So here, we might have T of 0, that's the set of all rational numbers. T sub 1 would be 0 sub 1, and, intersected with Q, of course, but now without the closure of this, which is just that, because it's a singleton point and it's already closed. Then, T2 would be our S again, set minus the union of the closures of all these S sets up to 2. Then if we wanted T3, we'd take this and remove all the elements in these sets. Then for 4, we'd say, oh, this with all these elements removed, and so on and so forth. So there are 3 things that we should note about this collection of sets T. First, X is equal to the union of them all, which should be obvious because one of the sets just is X itself, and all the rest are subsets of X. This means that the sets T form an open cover of X, as we sometimes say in topology. Furthermore, Tn is a point finite cover, in that any given point in X is going to be in a finite number of T sub n's. And this might be one of the spots where you have to convince yourself of the logical leaps. You can maybe think to yourself, oh, okay, I guess that if X is in a given, if X isn't in S, then it's just going to be in this one, and if X is in S, it's going to be in one of these, meaning that for everything, maybe it's in S of 10, meaning that for every n greater than 10, X is not going to be in that T sub n. So T sub n is a point finite cover. Finally, the set of points in X where there's an open neighborhood around that point, and that's just any old open set containing that point, that intersects finitely many T sub n's. So this can also be said as the set of points where the cover T sub n is locally finite. Point finite, locally finite, these are both kind of different extensions, variations of the notion of finite. That set is not dense. And again, this is something that's a little bit tricky to convince yourself of. You kind of have to refer to the fact that S sub I is nowhere dense. But moving on, we can now talk about the strategy. So let U naught, the very first play that player 1 makes, be any old non-empty open set that is not equal to X, and where this open cover that is point finite and locally finite in a non-dense set, where this is not locally finite. So maybe in Q, that would just be, if maybe that would be 0, 1, because for any point in 0, 1, well, you're going to have infinitely many points in a given open neighborhood of that point, and each of those points, they're going to have their own particular neighborhoods that T sub n that they're in. So this would be a good pick for Calvin's, I guess, first move. But really, a lot of things would work. Then, if the other player, player 2, Hobbes, chooses for their move on a given turn n v sub n, then player 1's next move is going to be the intersection of v sub n with the first set in this sequence T sub n, where the intersection of v sub n and T sub k is not null and is not equal to the set that you just got. Now, again, this might take a little bit of convincing for you. You have to think about, okay, exactly why, this set is always guaranteed to exist. It has something to do with the fact that, we're working in an area where T sub n isn't locally finite. And furthermore, we have to think about, alright, I guess you can't really repeat k's due to the way the sets kind of nest within each other, and furthermore, this kind of means that the k's can get infinitely large, arbitrarily large, I should say, and because T sub n is point finite, that means that any given x is going to eventually be left out of one of these, meaning that this intersection is going to be empty as player 1 desires. Now, player 2's strategy... Oh, before I get into player 2's strategy, actually, there's one thing I want to note. Because this is an if and only if here, and you can prove it the other way too. It's also very complicated. I'm not going to get into it this video. You can check some of the papers I've cited if you really want to look at that proof. In any case, because this is an if and only if here, because it is only on non-Baire spaces where player 1 has a winning strategy, we can use player 1 does not have a winning strategy in the game BMX as an alternate characterization of Baire spaces. And that's honestly pretty cool, right? Like, I don't know, these weird games that make no sense and that you can't even play, they end up being useful enough to describe perfectly this topological characteristic that, topologists find actually really useful. So, player 2 strategy now. Now, the space... Now, if we wanted to rigorously describe every single set where player 2 had a strategy, it would be very complicated. You'd have to get into, spaces of continuous functions between spaces, all that sort of weird mathematical meta stuff, and it would be more trouble than it would be worth. So we're just going to talk about what happens when we are dealing with a completely metrizable space as our X. Because note, by the Baire category theorem, all completely metrizable spaces, that is, topological spaces where you can define a reasonable measure of distance, and where, I think I've mentioned this before, but Cauchy sequences are convergent. In those spaces, the Baire category theorem says that they're Baire. So, if we're given a un that player 1 gives to us, all player 2 has to do is choose v sub n, whose closure is contained within u sub n, and whose diameter, that is remember we have distance between points here, so we just pick out the largest, the sort of maximum or supremum of the distance between pairs of points, just kind of the widest part of the set, you can think of it that way. We choose a set whose diameter is less than 1 over 2 to the n. So, the reason why this works, it's basically just that Cantor intersection theorem I mentioned earlier. You're basically squishing and squishing these sets that they technically aren't closed, but they all have closures that are, sufficiently small and within them so it still works. They're getting smaller and smaller, so their infinite intersection will be non-empty. The final thing I want to note in this video is that if we try to talk about the spaces on which, any old space where player 2 is not, where player 2 does have a strategy, then the term we use for that is weakly alpha favorable. Because sometimes player 2 is called alpha and player 1 is called beta when studying these games. Don't ask me why the first letter of the Greek alphabet goes to player 2 and vice versa. That's just how it is. But yes, as I mentioned before, the characterization of weakly alpha favorable spaces is pretty confusing, but it's terminology that I guess you should know if you're planning on studying these games further. I don't know if anyone watching this is, but, and the final thing I want to note is that, as before, there are spaces on which neither player 1 nor player 2 have a strategy. The class of weakly alpha favorable spaces is not the same as the class of Baire spaces. Once more, the Bernstein set, that thing you have to construct with the axiom of choice, is a set that it's a space that is Baire, but is not weakly alpha favorable. Alright, last episode coming up. See you then.